all of our discussion of transitions between individual energy levels would suggest to the naive listener that spectral lines would be infinitely narrow because the energy levels are reasonably well defined. But of course, they're not perfectly well defined, and there's a number of different factors that can set about determining the shape of a spectral line. Some of those are the quantum mechanical effects, and some of those are related to temperatures of gas or to other factors. So let's think a little bit in this lecture about what sets line shapes and how we can use the shape of the line to tell us something about the gas that it's coming from. So let me share my screen so that we can go. Okay, so in week 6, recall we discussed that the mean emission from a spectral line is defined as the integral over 0 to infinity of J nu d nu. And we let the emission coefficient, little j nu, be equal to h nu naught over 4 pi, say N2, the density of the atoms in the second state, times A21. And we defined a term phi of nu, where the phi of nu is the line profile. So this should all seem familiar. Phi of nu oops, I should write that differently. Should write that the integral of phi of nu, because it's a normalized function, the integral of phi of nu from 0 to infinity is equal to 1. And this just looks like some function, which I'm drawing as broadly Gaussian at the moment, and it's defined at nu 0, and this is my phi of nu. So what sets phi of nu? And that is the whole topic of line shapes. So there's a couple of different things. The first one that we'll consider, and the easiest one to think about, is Doppler broadening. So first, Doppler broadening. So for this, you consider that frequency minus the central frequency is related to the velocity distribution, Vz, over the speed of light. So for velocities in the range Vz to Vz plus dVz, is proportional to the exponential of the mass of whatever this particle is. So the mass of the atom over the temperature. And so from that, it follows that the line profile shape is equal to 1 over delta Vd square root of pi, delta nu d, that's the Doppler width in frequency, nu d, e to the minus nu minus nu naught squared over delta nu d squared, where the Doppler width, delta nu d, the Doppler width, is related to the central frequency times the square root of 2kT, which is the temperature of the gas divided by the mass of the atoms. So all this says is that a given atom may be emitting at a particular frequency, but if that atom is moving away from us, then it's Doppler shifted, or if it's moving towards us, it's Doppler shifted. And we have to consider the population of atoms and their movements as shifting that line just a little bit from one direction or another, and the width of how much it's shifted, or the distribution of how much it's shifted, is set by the temperature of the gas, which distributes the velocities of those particular atoms. So Doppler broadening is a very common effect. I use it all of the time in atomic hydrogen, and it adjusts the width of the line from being, say, for atomic hydrogen, almost perfectly narrow, extremely narrow, smaller than we could possibly detect with any of our telescopes, to something that is on the order of a few kilometers per second in velocity width, or several kilohertz in its width. Okay, so this gives us also a line center cross section. So this is the cross section for it being at that exact line center, and that's B12 h nu naught over 4 pi phi of nu naught. So that's the standard way of writing this relationship, and times an oscillator strength F12 1 over delta nu d, the Doppler width, times the square root of pi. So that's Doppler broadening. That's the first example that we'll talk about. The second example, or the second reason for having a line width that is more than infinitely narrow, is natural broadening. And this comes about because of the uncertainty principle, that the energy times the time, delta E, delta T, on the order of h bar. So there's a spontaneous decay rate not all of our electrons would decay at exactly the same perfect time. There's a certain rate of their decay, which is given by gamma is equal to the sum over the n prime state of the Einstein spontaneous coefficient, a n n prime, where in this case n prime is the lower energy state, because this is a spontaneous emission process. And this gives a natural line width, a line profile, which is equal to gamma over 4 pi squared over nu minus nu naught squared plus gamma over 4 pi squared. And this is a so-called Lorentz profile. And you'll see that term thrown around quite a lot when we talk about spectral lines in their detail. Now, the combined Doppler plus Lorentz is described as a Voigt profile. And that's also quite common in the situation where the Lorentz profile with the natural broadening is of the order or similar to the Doppler broadening. You need to put the two things together and use a Voigt function for the entire situation. So let's put this all together. In our final brief little lecture, we'll think about how we can put together our line widths, our photoionization, and what it means for considering radiative transfer. So I'll stop there and we'll pick up on a final little lecture after that.